So welcome once again. This is the lecture number 6 of the deep learning course. In this session, we are going to see more about the optimizations, and actually optimization, teaching optimization is very important, and this is going to be the final thing that we are going to touch into this course with respect to the optimization. And hope you would enjoy and understand that these things are why these things are important. So in this session, initially I would show you that some of the some of the some of the important jargons that the people use. Just sake of completeness, I just want to bring in front of you. So we would study about the confusion matrix. So to understand that what is the confusion matrix and what are its parts, then we would see that what is the linear programming problem and what is the multivariate optimization problem and how we can solve. What is the Kkt condition and why it is important in our scenario. So let us start this discussion by bringing you in front of you a small problem, and this problem is very simple. And let us read um, um, along. So let us consider 100 images. Consider 100 images in a box. Let's assume that there is a box, and there how many images are there? 100 images there. And the condition is this: that 30 of them are containing the lion. So how many images are there? 100 images are there. So there are 30 images where there is lion. So we can say that there are few more images. How many? 70 images where there is no lion. 30 images contain lions and 70 images that does not contain lion. Let's assume that we have developed a robot, and we have asked from that robot that go and search for the for this particular box and give me all the images where there are lion. This is the problem. I ask from the robot that give me all the images where there is lion. Let's assume that my robot has picked 60 images out of this. So he had brought 60 images to me, and my robot was thinking that looks like that all of them are going to have the all of them has lion. Okay, because robot has given that to me. So definitely you can see that's only 30 images were containing lion. Now it is going to give me 60. So there is a problem. There must be the problem. So if I identified and seen, if by myself, if I have verified and saw, oh my God, 40 images are such that where there is no lion. Looks like then what does it mean? That 20 images contain lion and 40 images does not contain lion. So this is what the scenario is. I had a robot I had deployed on this particular box, and in this particular thing he have given me 60. Out of them 40 was having what? 40 was not having the lion and 20 of them were having lion. So I can also see the second part of this particular problem. I can say that 40 he has shown to me. So 40 he have not shown to me. He was thinking that there are some other set of 40 images where there is no lion. And if I see that, if I consider that particular part, you can see that since only 20 images he have shown me, so he have missed 10 images. Those 10 images would be there, and there would be another 30 images where actually there is no lion. In these 30 images there is actually no lion, but in 10 images there is lion. Okay, this is what the scenario is. So if you recognize this scenario, so you can make a table of this particular kind. This particular kind of table you can make. This table is called it has a very important name called it is called the confusion matrix. And this is a very important table in terms of the machine learning, and it gives you the two perspective of your things. One is the ground with respect to the ground truth and with respect to the experiment. Here we are assuming that my problem is the classification problem, and there are two classes only. There is lion or not lion, and true and false, 0 and 1, -1 +1. Two classes are only there. So I can say that the one class is true class, means there is a line, and the class is false, means the line is not there. So if we go with respect to the ground truth, so if I go into this particular direction, so if I go in direction true, means how many true things are there? So you know that how many lines were there? 30 lines. So if I go into this particular direction, means from the ground truth I get 30 images where there is true. Similarly, for the false one, if I travel in this particular direction, 40 plus 30, it is 70 images there where there is a false. But from the experiment perspective, if I ask with respect to the robot, so I go down, I can see that he has given me 60 images, and according to my system 40 images were such that where there was no line. So 40 images, this is what it was. With respect to the experiment, how many of them are true? 60. How many of them were false? 40, with respect to the experiment, because this is what my robot was saying to me. What is actually 30 plus 70? This is the actual thing. So if you look closely, so as we have seen that this table, we have also seen that we can divide this 30, 40 and 60 into two parts. And this 60, as for example here we have few minutes back said that 40 of them were not having the line, means 20 of them were having line. Into the similar way, into the false one, 10 are going to have the line, and 30 which he have left, it is not going to have the line. So if you analyze it, you can say that here is a problem, because this is the part where there is a problem. And because he have what he has what my system has done, he have accepted them. Okay, my system had accepted these items, and similarly these items my system has rejected. Okay, my system has actually rejected. These are the two places there is a problem. So since there it was a problem there, these accepted are actually false accepted, and similarly these rejected are also the false rejected. This is the false rejected one. In the few lectures back we have discussed that false acceptance is called type 1 error, and this is called the type 2 error. Two kind of errors my system has actually done. So this particular table actually bring these things very nicely. Okay, this particular table bring these perspective very nicely. So whenever you are actually conducting any kind of experiment, and if you run a code into the Python, you would be if you run the analysis part out of that, so this table you are definitely going to see. Once again, how many true positive things are there? Okay, accepted means they are positive. Okay, so accepted means they are positive. True positive means things which are actually my system has actually truly identified. True positive is 20. You can see that true positive is 20. The places where my system was correct. True negative, it was 30. So system was correct in telling that these 30 in these 30 places there is no line. So this is the true negative. Type 1 error, false positive. You can see that the 40 is the false positive, and type 2 error is the false negative. It is a 10. Any problem in this? In the last class also we have discussed that this is a more difficult problem, means this is a more severe problem, because we don't want anybody who is actually not authorized to enter into the system. It is fine that if somebody who is actually okay, he is rejected, he can go for the another attempt, but here it is a big problem. So if I ask you this thing, that how good my system is, so can you tell me that how good my system is? You can see that the places where my system is correct, means here my system is correct, and here also my system is correct. So there are few other settled notions. So we can represent this thing, how good my system is, using the term called accuracy. And accuracy is 20 plus 30 divided by 100. Out of 100 cases, 20 plus 30 is what my system is going to be there. So this is the equation of the accuracy. Another notion of there is another notion called precision. Precision means the things which my system is telling, in which how much good the system is. So you know that my system is going to tell this thing as an answer. He has given me this as an answer, and out of them only 20 was actually correct. Okay, so my system precision of my system is 20 by 60. Precision of my system is 20 by 60. This is what the definition of the precision is. And similarly there is another notion called recall. Recall says that because I have intended my machine to find out the line images. Out of these 30 images, how many images he have returned to me? 20. So recall was 20 divided by 30. 30 is again 20 plus 10. So using this table again, I can find out that what I may recall specifies that for the task for which I have actually deployed my system, how good my system is. Another notion is the specificity, that is the true negative rate. So true negative again tells that how good my system is telling that negative is actually negative. So you can see that out of 30 divided by out of total things that was actually negative, 40 plus 30 was actually negative. Out of them 30 my system was able to tell that into the correct way. Sometime when you want to you define your system, you have to specify all these values, and specifying all these values and then getting out any kind of sense sometime becomes very difficult. So people want to combine these things, and there is a notion called F score. And F score says that if you combine the precision and recall these two values, you take these two values and take the average of these quantity, it is called the F score. Another is called the F1 measure. Please note that there is a difference. F score and F1 measure. Another way to combine these two is called the F1 measure. And this formula is again there is a different kind of formula that F1 upon F1 is equal to 1 of precision plus 1 upon recall. So if you have a system, you find out that what is the value of precision and recall, you put into this formula and solve this thing to get the value of F1 measure. So I just brought this slide to just complete all the type of mm, system related jargons in front of you, so that you become accustomed and you understand all these things in a correct manner. Okay, hope it is clear to you. Any questions? If you have, please let me know. It is clear? Yes or no? Yes?
Yes, sir.
Correct. Clear. Great. Now let us look the optimization more closely. And you know that what do I mean by the optimization? You know that generally we have a equation. For example, here is an equation written, and and whenever in our study we talk about any kind of optimization, we are actually dealing with the multivariate optimization. Means multiple attribute or multiple values would be there. So if I want to, for example, if I define a variable z using this particular equation, and here multiple attributes are x1, x2, these are the attributes, and I define a formula, and I want the optimized value of this. Optimized could be means maximum or minimum value. So this is the equation. For example, I want to find out the maximum or minimum of this particular quantity. So sometime this you cannot do this, all the values are not available for you, and we also define some kind of constraint, such as if I define that using x1, x2, x3, if I define this as a constraint, I say that sum a11 multiplied by x1, a12 multiplied by x2, a1n multiplied by xn should be less than b1. And similarly here I can provide multiple equations that can say that providing this constraint, I want to find out that what is the maximum value or minimum value of this particular quantity. So this kind of formulation is called the linear programming formulation. Here this is called the linear programming formulation. Let me just quickly, just for the sake of your understanding, let me create a formula. For example, I say that z is equal to 3x1 minus 2 3x1 minus 2x2 plus 4x3. I want to find out the maximum value of this particular equation, provided the constants such as x1 minus x2 should be less than 3, less than equal to 3, and x2 plus 3x3 should be less than equal to 10, or such that some equation that I'm going to write. So this is an example where I have actually put the values into this particular equation, and now my question is that can you give me that what is the minimum value over here? This kind of formulation is not new for you. You have, even from the class 12 student these days, they study this thing. It is called linear programming. Okay, this is called the linear programming formulation. And to find out the solution, you know that using these kind of equation, you actually try to build a feasible region where the solution is there. For example, all these things are a kind of line only. So you, with respect to the every equation, you are going and draw a line. For example, I draw this line and multiple lines I draw, and I say that my equation should be between these things. So ultimately you reach to this particular area, that only feasible solution would be into this particular region only. And in this particular region, mostly the answer that is going to be, it is going to be where, at the extreme point, somewhere where the corner points, it is going to be there. So you know that all these things using sometime called simplex kind of method, you can apply and you can find out the solutions into these cases. What is the important in this particular formulation is this, that this formulation is very simple, and where these all these things are actually linear, means x1 is there, x2 is there, x3 is there, What do I mean by this? I say that I have not written something that e to the power x1 minus 2 log x2 like that. If I write the equation like this, then it is actually more general condition, and most of the time we would be actually in this scenario only. Not every time we are going to get this nice linear equations. So this is the more general condition. So if we are not into this kind of big problematic situations, so we can apply simplex kind of method and find out what is the solution. Um, Here I just wanted to mention one more point, that here something is written programming, but it is again a misnomer. There is no programming here. Just people has given the name. There is nothing programming coming over here. So all right. So but however, as I told you that most general condition are such that the equation are going to be of this particular this particular kind. So my objective would be to give you an idea that into the multivariate situation, when your equation is not linear, how can you find out the solution? Okay. So this particular scenario is called the multivariate optimization. Okay. This is called the we study into the multivariate optimization. And here again our objective is this, that some function is given to me, and we want to maximize this particular quantity subject to some constraint. For example, this is a constant where I say that there is some other function with respect to this, and we want this value to be constant. Again, just for the sake of example, I can say that fxy is equal to 3x square minus 9x cube plus e to the power xy. I can write the equation like this. I want what is the maximum value of this particular quantity. Okay, function of xy. So you see that how weird kind of function it is. And then I can give the constant. I can say that x square plus y square should be less than so should be equal to 20, should be equal to 20. For example, I give this kind of condition. So this is a very general kind of condition, and my objective is in this session to give you some idea that how we can solve this kind of problem. All right. So let me start by saying you this thing, that 1 minute. Let me draw something like this. Let me say that here is a x direction and here is a y direction, and let me say that in the z direction I am going to plot the function of xy. Okay. Let me show you that how the curve is going to be. So let us just take some example. And here if I say that I pick some value of x and some value of y, I put that value into the equation, and by this equation I get some because I would be getting some value. So that value I would come here, and I would go upside and I would put that a point over there. Do you understand what I'm telling? I am telling that for all values of x and y, you find out that what is the value of fxy, and you put those things over here. So by this you would be getting some curve. Do you agree? Yes or no? You would be getting a kind of surface over here. Do you agree or not? Yes or no? Can anybody write yes? Yes, you would be getting a surface. Just I want to give you just the sake of example. Let us consider that that particular surface is a circle or a ball. Can you consider a ball over here? Just assume that there is a ball. Okay. Let's assume that the function is such that when I plot this particular function into three-dimensional space, it looks like a ball. If I ask you, can you give me what is the point where this particular function is minimum? Can you give me? You can, sir. If it is a ball, the minimum would be here. Everybody, okay? Yes or no? The minimum would be at the bottom point. It would be here. But if I add one more condition, if I say that no, you cannot travel anywhere, you can only travel on this particular surface. If I draw a surface, because you know that this another equation is going to give you have to be equal, and equality means that it is again going to represent some kind of surface. So you can only move on this surface. If I say that you can only move on this surface, then whether your answer again would be on this particular small point? No, because then you can assume that you have an orange and you have cut that particular orange. So minimum would be on this particular plane only. So it would be somewhere here. Am I right? Am I right? It would be somewhere here based on the slope of this particular uh, surface. It could be here or here, somewhere on this particular place. Yes or no? Yes, it would be somewhere here. So this condition actually, these two things try to understand. The first thing defines the curve, and the second thing defines the surface on which you can move. And based on that, you have to now find out that what is the minimum point. Okay. So hope you understand this particular scenario. So let me show you with respect to a two-dimensional space only. Let me say that here it is the value of x and here is the value of y. Okay, and let me restrict myself and give you this thing that let's assume that I am on a surface. Let's assume that it is some surface on which I am. Okay, and you know that anywhere if there is a surface, you can assume that it is a plane surface. You can rotate yourself in such a way so that you are into the plane surface. So can you always make this? Is it a not bad assumption? You can always make it that you are onto the right thing. Now let me give you something. So on this particular surface, let's assume that the minimum value is here or the maximum value is here, whatever you want to optimize. Let's assume that the minimum or maximum value is here. If I ask you that if it is the minimum value, what is the, and let's also assume that minimum value is 100 of what? Of this function. Minimum value of this function is at this particular moment. If I ask you that what is the value here, and let for the sake of simplicity, let me say that it is the max value. Okay, let me say that it is the maximum value. Maximum value is 100, and this is on this particular point. If what is the value on this particular point? Can you tell? Can you guess? Anything that is actually, because it's a maximum, it could be maybe 90. Yes or no? It could be 90. Yes or no? Yes. Can anybody type yes? Yes. So if here is a 90, what would be the value just beside it? This particular point, for example, here if I search any point, can I also get a point here with the value 90? Yes or no? Yes. Can I get another point here with the value 90? So I can find some other points also that are going to have the value 90. So I can create a contour around it which has the value 90. None of these points would be value 100, because you know that if the value is going to be increased, the values, let's also assume the space is continuous. Okay, because if the space is not continuous, you're not considering that particular thing. Okay, then it is discrete. You can also think that the discrete is a only just a way of looking that how with what quantum you are actually moving. So we are assuming here that the function is continuous. Okay, all right. So this is a contour that has the value 90. It is looking like ghost. Okay, so let me make it good for you. Again, it would look like ghost. I cannot do anything. Okay, so what would be the value here? Can you tell me? It is far away, maybe 60. Okay, so can I also get the same kind of something here also? A contour related to the 60. What would be the value here? See, you can see that it is in between the two contours, so the value could be greater than 90, but the less than sorry, greater than 60 but less than 90. It could be 80. So it could be a contour like this. It would not touch here. So oh my god. So it could be something like that. Okay. So similarly with the respect to 70 also, I can find out some contour here. Okay. With respect to other values also, I can create multiple contour. Now if I, as we have solved few minutes back, that the maximum value is here. Okay, and I was hunting for this thing, but now if I say you that you cannot move because of some condition, I give you another condition, I say that you cannot move everywhere, if I say that you can only move on this particular line only, if I say that you can only move across this particular line only, so with the, if I don't specify this line, what was the maximum? Maximum was 100, maximum was 100, maximum was 100. But if I specify this line, can you tell me what would be the maximum value? Just have any guess? Any guess? Just type. So you can see that 90 is here. So, and it is some maybe 93, then it would be something around 93. It is going to touch this particular thing. Makes sense? It is not 90 because after 90 there is some contour. It is going to touch that thing. So it would be something 90 plus. Makes sense? Okay. What is the property of this particular curve? If you try to see, you can analyze this particular thing, that on this particular contour, if you want to see that what is the gradient direction of the gradient, you can see that the direction of gradient of this particular contour is this, and the gradient of line is this. Here the gradient is this and gradient is this, gradient of line is this, gradient of contour is this. When they have the different directions, what is going to happen, that this line is going to cross that particular contour. So it is always going to happen for all the things, it is going to happen, but the place where it is going to touch the thing and go away, at that point the direction of this particular direction of the slope of this particular line and direction of the slope of this particular contour is going to be the same. Make sense? And after that, again it is going to be happen the same thing. The contour is into this particular direction and line is into this particular direction. So there would be some point where this condition where the minimum is going to happen. And what is the property of that particular thing, that if you find out that what is the slope of the f function, and if you find out what is the slope of this particular line, that is the condition, they are going to be there aligned, they are into the same direction. If they are same direction, we can say that if I multiply, because their value would not be the same, so if I multiply with some kind of multiplying factor, maybe lambda, so I can say that they are going to be the same. This is what the condition is. Make sense? Yes or no? Yes or no? So this particular condition has been highlighted into the Lagrange multiplier. It says that if this kind of condition is specified, that I want to find out the maximum value with respect to some kind of other equation, it actually means that the slope of f minus lambda times slope of g is going to be 0. This is how we are going to define this particular condition. The point that is going to satisfy this thing going to have this particular property. Let me solve this particular, let me use an example and show you this with respect to an example. And this is what example, this is one example that I have. Let the cost of producing x amount of a product A, let's assume that there is a factory that is going to produce A and B, two items it is going to produce, and I want x amount of A and y amount of B. And let's assume the cost of producing x amount of A and y amount of this is 6x square plus 12y square. Let's assume that this is what the cost is. Okay, and we want at least 90 items to be produced. Means we want what? That x plus y is equal to 90. We want what? That x plus y should be equal to 90. So how can we model this thing into Lagrange multiplier? Lagrange multiplier says that you write a Lagrange equation that is going to be that you want to represent. First you write the Lagrange equation that is going to be with respect to the function. You write 6x square plus 12y square, okay, minus lambda time of x plus y minus 90, because this equation is x plus y minus 90 is equal to 0. You can always make like that. So you create the Lagrange equation like this, and then you find out the derivative. What is the derivative of L with respect to x? What is the derivative of L with respect to y? And what is the derivative of L with respect to the lambda? Can you solve this thing for me? So so let us try to find out these values. So del L upon del x is going to be what? You just integrate, because you know that in this particular formula here is a x, and here also is a x, so you can write the 12x minus lambda. Am I right? 12x minus lambda. Similarly, del L upon del y, you integrate this thing 24. What is this? 24y minus lambda. What is del L upon del lambda? You can see that there is no lambda term here, so it goes away. Only this remains. So it becomes minus of x minus of y plus 90. Am I right? Upon del lambda. And if we want to do the optimization at the point where there is an optimization, the derivative of that particular quantity del upon del x is actually 0. So if the derivative is 0 on the optimization point, then we can equate this thing equal to 0. If I equate that like this, I can say that x is equal to lambda upon 12. Similarly, here I can say I can also say that on the optimality point, I can also say that del L upon del y is going to be 0. And then by this, I can say that y is equal to lambda upon 24. Am I right? Lambda upon 24. If I put this thing into this equation again, this equation also have the value is equal to 0 because of the same reason. I can say that minus lambda upon 12 minus lambda upon 24 plus 90 is equal to 0. So hope you can solve it, and by this you can give me the what is the value of lambda. Can you tell me that what is the value of lambda for me? Anybody? Looks like that it is going to be, because you know that in 24, so I can write
720.
3 upon this, and lambda comes out to be 30 multiplied by 24. Use this value, put it here, and get the value of x and y. And by this, you are going to see that the value of x and y are going to be what? X is equal to 60 and y is equal to 30. So this is how you solve this particular problem. Here, you create this particular value you wanted to optimize, subject to the condition that x plus y is equal to 90. So you have solved this thing using the Lagrange multiplier. Let me show you one more example to just for the completeness, because here you can think that the condition was actually x plus y is equal to 90. It was a linear equation. You may think that can we also put the nonlinearity at that particular place also. So let me define this particular function of the three variable x, y, z, x square plus x plus 2y square plus 3z square, like that, x square plus x plus 2y square plus 3z square. I want to optimize this particular value subject to the constant what? That x square plus y square plus z square plus 1 is equal to 1. Again, the same way we can write the Lagrange equation by saying that L is equal to this particular quantity plus lambda time, take it this particular side. This equation we can write into this particular way. Same way we can again find out the derivative of the L with respect to x, y, z and lambda. With respect to the x, you can say that the derivative is 2x plus 1 minus 2 lambda x, 4y minus 2 lambda y. You can find out the derivative, that is not a big thing. So if you find out the derivative like this, so what it gives, for example, here you get 4y minus 2 lambda y is equal to 0, because why 0? Because when it would be optimized, the value would be 0. Here you can say that you can take 2y common, you can say that 2 minus lambda is equal to 0. And if you want to make the 2y minus, sorry, 2 minus lambda is equal to 0, it means what? Either y is equal to 0 or lambda is equal to 2. This is what the condition is. Similarly, if you pick this particular equation, it is 6z minus 2z, 2 lambda z. It gives 6z, sorry, you can take 2z common. It is 3 minus lambda is equal to 0. It gives you that either z is equal to 0 or lambda is equal to 3. These are the two conditions that you get. So using these two conditions, you can create a set of equation, because we are interested to find out what is the value of x, y, z and lambda. Actually, we are not interested into the lambda. We are only interested into x and y, x, y and z, because this is what the function is. But we are writing z because we are also have a slack variable right now. So how can I find out the value? When the y is equal to 0, I can take the z is equal to 0. So y is equal to 0 and z is equal to 0. Another condition could be that I take y is equal to 0 and lambda is equal to 3. So y is equal to 0 and lambda is equal to 3. Third condition could be that lambda is equal to 2. Once again, lambda is equal to 2 and z is equal to 0. So what it is? Lambda is equal to 2 and z is equal to 0. Another condition could be that z lambda is equal to 2 and lambda is equal to 3. So this is the absurd condition. Both the equation are giving, one is telling 2 and other is telling 3 simultaneously. They cannot be true. So these are the three conditions that I have. Okay, so let us further solve this thing to find out something useful. So if just pick this particular formula, okay, pick this particular equation where y and z is equal to 0. So put this thing into the third equation. Where is the third equation? This equation, x square plus yx square minus x square minus y square minus z square plus 1 is equal to 0. And here y and z is equal to what? What are their value? Y and z are 0. So you put here, they go away. So you get x is equal to plus minus 1. Am I right? Okay, so x is plus minus 1, and let me remove this thing from the second condition. Value of lambda is equal to 3. You put this value into this particular equation. So what you get? 2x plus 1 minus 2 lambda x is equal to 0. So lambda is equal to 3. So you say 2x plus 1 minus 6x is equal to 0. So it is going to be 4x is equal to, am I right? Am I right? 4x is equal to 1, x is equal to 1 by 4. Am I right? So x is equal to 1 by 4. I got the value of x and y. Again, I can utilize the same equation that we utilized earlier to find out the value of z. In using this particular formula, once again, what the value of x is equal to minus 1 upon 16. Yeah, x square is there, na? 1 upon 4 becomes 1 upon 16. Minus y is 0. Minus z square plus 1 is equal to 0. Can you tell me what is the value of z? So z comes out to be, am I right? Plus minus under root 15 by 4. Is it right? Plus minus under root 15 by 4. Okay. Okay. So let us get forward. Again, third equation. Here the lambda is equal to 2. Let me put it here because this is my favorite equation. 2x plus 1 minus lambda is equal to 2 minus 4x is equal to 0. So 2x is equal to 1. Then x is equal to 1 by 2. So I can say that x is equal to 1 by 2. Again, I put this into this particular equation. So it becomes minus 1 by 4. What is the value of y? I don't know. Minus y square. What is the value of z? You know that in this particular case, z is provided as 0. So I put z is equal to 0 plus 1 is equal to 0 because at the optimization point, this equation is going to be 0. So what I get? Can you help me find out what I get? So it is, I think, y square is equal to 3 by 4. Am I right? So it becomes a plus minus under root 3 by 2. So this is what we get by solving this thing. So if I get this thing, I am not interested into the value of x lambda. Okay, we are only interested into the value of x, y, z. So let us first consider this thing here. What is the value? X is equal to plus 1 and x is equal to minus 1. With respect to this, y and z are 0. Y and z are 0. From the second equation, it is x is equal to 1 by 4, y is equal to 0, z is equal to plus under root 15 by 4 and minus under root 15 by 4, 0, 1 by 4. Okay. And from the third equation, I get 1 by 2 plus under root 3 by 2 minus under root 3 by 2, 1 by 2, 0, 0. So these are the 6 points I get. Let me call this point as P1. Let me call this point as P2. Let me call this point as P3. As this as a P4, this as the P5, this as the P6. So what is the problem? If you, for example, this is the value, na? X, y, z, you put these values x, y, z into this particular equation and see that what is the value of this particular function. You can put it here because x, y, z, what you need x, y, and z to find out what is the value of this particular equation. You put this equation over here. So what is the value? Can anybody help me? So there is a cheat sheet. Okay, at the bottom side you can see that I have done all this computation earlier also. So the value of P1 is this, P2 is this. So what is the value? So it is showing that evaluate P1 is equal to 2. So you get 2 from here, and F2 is equal to 0 from here, and since here you get 25 by 8. Here you again get 25 by 8. here you get 9 by 8, here you get 9 by 4. These values you are going to get. All right, so which of them are minimum? This is the minimum one. Which is the maximum? 25, 28, but upon 5 is maximum. So you can find out, as we have solved, that maximum is 25 by 8 and minimum is 0. At what point? By this you can solve and tell that which are the points which are going to be maximum. So this is the method that we have just discussed, is called the Lagrange multiplier. By this we can find out the optimal value of a optimal value and the point at which the value are optimum for the given multivariate problem. So a problem is given, subject to the constraints, and now you can solve this thing. Once again, if multiple constraints are there, this was the one constant. If multiple constraints are there, then what would you do? Instead of one lambda, you are going to write lambda 1, lambda 2, lambda 3, and you are going to multiply with respect to each of them, and you can formulate the problem in that particular way. So general multivariate optimization problem may also have some kind of inequality constant. For example, here we have into the Lagrange multiplier, the condition was this, that this should be equal to something. But into the general scenario, it may be possible I can say that the G is less than something. Okay, into some situation, it may also be possible that there is something less than this. So to solve this thing, there was a mathematical, there was something, some mathematical trick was actually discovered. They told that instead of using this formula, I am going to say that here I am going to add something, slack variable. I am going to call that as slack variable. That I say that G square plus some Sj square. So if Sj has some, it is a slack variable. If I put a square of that thing, means that it is going to be the positive. If something was going to be less than this, then if I'm adding something, I can always make that 0. So earlier I only wanted to find out the value of x, y, z. Now in this new formulation, along with this, I also want what is the value of S1, S2, S3. But when my solution is going to come, I would neglect this thing. I would only report this as an answer because nobody is interested in that. So I can include a slack variable in my formula, and and all of you understand that if there is a formula, for example, if somebody says that 3, if instead of less than, somebody says me that 3x square plus 4x 4xy is greater than equal to 0. Somebody says like this, I can always convert it. Minus 3x minus 4xy is less than equal to 0. So without loss of generality, I can assume that all the constant can be converted into this form. If all the constants can be converted into this form, I can add a slack variable and I can convert into this particular form. Then what does it mean? That we are with this particular formula and this particular formula. Now we can apply the same Lagrange multiplier system over the thing and get our solution. So once again, how we did there, as I told you, that now we can, with the slack variable, we can define the problem in this way, that use this particular function, and then for all the constants, if there are n number of constants, for all of the constant you multiply with the ji and put this particular formula. Wow. And it is coming from this particular formulation. Again, Lagrange is defined using this particular formula. Any problem in this? Yes or no? Yes, it is fine. I told you that if the condition is if the general optimization problem is given like this, then you can convert this particular problem into this particular Lagrange representation. Yes or no? Yes? Can anybody write yes? Nobody is writing yes. Can anybody write yes?
Yes, sir.
Okay, you can just type, yeah. So we can convert. You have seen that if it is greater than this, you can multiply by minus, and this becomes into this formula. Then you can add a one more variable, that is a slack variable. Then it becomes equality constant. Using the equality constant, this is how we write the equation with the Lagrange thing. So this is the condition that few minutes back we have seen, that Lagrange equation is like that. How can you solve that? You know that to solve this, again you have to find out the derivative of this particular thing with respect to x, with respect to lambda, with respect to the sj. So you find out the derivative with respect to xi and in equate it to the 0. Find out the derivative with respect to lambda and find out the derivative with respect to the sj. And once again, it is not very difficult to see that if you want to find out the derivative with respect to the x, So this term goes away, only the derivative of this thing remains. So it is a derivative of this particular term and then the derivative of this particular term. This is how the equation comes to you. Any problem in that? If you find out the derivative with respect to the lambda, then this term goes away, this also goes away, then only the derivative of this thing, no, this doesn't go away because it is outside now. Only remaining thing, only inside thing remains. So you say that gj x plus sij square is equal to 0. If you do the derivative with respect to the sj, then this goes away, and only the derivative of lambda time sj is there, because 2 comes here, 2 multiplied by sj. What is the derivative? Let me just say that del upon del sj. So you know that this term would go away, and multiplication of this with this actually goes away. Lambda can come here. You can say that lambda j multiplied by derivative of, because it becomes constant, sj square. Derivative of sj square is what? 2 multiplied by sj, and then the equation becomes that lambda j multiplied by sj 2 is equal to 0. Then you can remove this 2 because next side it is 0 only. So you can say that lambda j sj is equal to 0. These three conditions has a name also, and the name is called the first condition is called the optimality condition, the second one is called the feasibility condition, and third one is called the complementary slackness. Together these three conditions are also called the Karush-Kuntukar condition, and in short they are called Kkt condition, Karush-Kuntukar condition. And this condition is necessary if you want to find out any minima for the set of equation. Okay, this Kkt condition actually is a necessary condition, means that it should be there if you want to find out the optimal thing. However, this is not sufficient. The things would be sufficient if the function that actually you are going to consider is actually a convex function. If this function, the function that you are going to consider, is actually a convex function, then this Kkt condition becomes sufficient also. Okay, just for the sake of completeness, I wanted to tell you that what do I mean by the convex here. Okay, and later point of time also we would be requiring this thing. So let us assume that you have a function. Okay, let us assume that you have a function fx. With respect to the x, there is a variable x. If you draw this function, the function comes like this. Okay, so when I can tell this function is a convex, so there is a specific condition. You know that you can pick any 2 points, x1 and x2. Let's assume that I pick any 2 points, x1 and x2. It is not necessary to be one side of the minima and other side of the minima. It is not required. You pick any 2 points and I say that it is x1 and x2. So any middle point if you want to find out. So there is I can write that, for example, I want to find out this particular point. I can say that some lambda time x1 plus 1 minus lambda time x2. I can say that this is new x dash. Okay, I can say that this is x dash point. I can find out like this. Okay, where lambda is going to take the lambda is going to take the one minute. Lambda is going to take the value from 0 to 1. If I put lambda is equal to 0, then it becomes what? X2. If I put lambda is equal to 1, then this becomes 0, it becomes x1. Okay, so any point if I want to find out in between, I can use this equation to find out any represent any point. So if I ask you that what is the value of this function on this particular point, so you can say that f of, put this point, lambda time x1 plus 1 minus lambda time x2. This is the value that this particular function has on this particular thing. This is the value. Okay, so what was the value on x1 of this particular function? It is fx1. What was the value on x2? It is fx2. In the same ratio, if I come at this particular place, means if I draw a line from joining these 2 points and I want to measure that what is this particular line is, I can again do the same kind of scaling, and I can say that lambda time fx1 plus 1 minus lambda time fx2. I can say that this is the point like this. If we consider these two quantities, this quantity and this quantity, So this second quantity should be greater than the value of function. Mean the value of function should be lesser. What do I mean by this? I say that the value of function, this value should be lesser than this particular quantity. Should be lesser than this particular quantity. This should be lesser than or equal to. If this condition is satisfied, I say that the function is a convex function. This is what the property. This is the property of a function that tells that the function is actually the convex function. If the function is convex and we find out the we solve this equation to find out the solution, then my solution is going to be give me the minima thing. This is called the Krush-Kantukar condition. Okay, so why are we taking square of slack variable? Okay, so this there was a question, so I think I missed that thing. Let me just tell you that here you are asking that why I'm taking square of a slack variable. The question is this, the point is this, that is this particular slack variable can be positive or negative also. Now just make 100% sure that even if this value is actually negative, square of this particular quantity, if I'm going to add it, it is going to be added something positive only. In this equation, this value should be less than this. Okay, if so, and I want to make it 0. So what need to be added over here? Something positive need to be added here so that it becomes equal to 0. So to make sure that only positive things are added, the technique says that we have to apply this square. Rohit, is it clear? So this is that's all for today. Thank you very much for joining.